Hey guys, welcome to another video on A-level physics. And this video will be about the electronics topic, which in my opinion is one of the more difficult chapters in A2 physics. Hopefully this will be a very thorough and detailed video covering all of the syllabus content in sufficient detail. At the end, I will also include some questions from the past paper and a few books. So the first thing you need to be able to do is to recall the main properties of an ideal operational amplifier. And if this is the first time you're doing this topic, you wouldn't even know what an op-amp is, let alone an ideal op-amp and the properties associated with it. Right? So you need to know the main properties. And the important part of this point is that they're asking for the main properties of an ideal op-amp and not just a realistic op-amp, that is the one that you will actually use, that actually exists. So let's come back over here. And this book is actually pretty great for a lot of chapters, including this one and the one on communication systems. So a lot of you must be familiar with sensing devices, like in ACs, because in AC there is the internal circuitry of an AC constitutes a sensing device which is able to take note of changes in the temperature, right? Because at a particular temperature boundary, if the temperature were to cross it, it would either switch off the AC or switch it on, right? So there is obviously a sensing device that is able to detect that threshold temperature, right? And then there's going to be an output device which is going to receive the voltage signal from the sensing device and then do something, right? In this scenario, that doing something would be turning on or turning off the AC. But it's not quite as simple as you would think. The voltage signal from the sensing device has to actually be processed, right? And that is what basically an op-amp does. It processes sensor voltage. So if you're making notes, I'd suggest you write it down. For the processing of sensor voltage, that is the voltage signal from a sensing device to which the op-amp is connected. So there are a lot of different examples of various machinery that makes use of an op-amp for this purpose. And what exactly is an op-amp? I get it, it processes stuff, but what exactly is it? They're probably not going to ask you that at this level, but it's actually an integrated circuit. And integrated means like it has a lot of different individual components and they're sort of like together. So it's an integrated circuit that contains about 20 transistors. Transistors are again something you would be unfamiliar with at this level, along with resistors and capacitors. So it's complicated stuff. And it's an integrated circuit because all of the components are formed on a small slice of a semiconductor with connections to enable the op-amp to be connected into a circuit. And the whole of the integrated circuit is encapsulated. So this isn't really relevant. So now we know that its function is the processing of sensor voltage. Now you need to be really familiar with the symbol And why is that important? Because you have to oftentimes make it. In an exam question, they're going to ask you to draw a op-amp in a circuit, right? So in your notes, I'd suggest you draw it big and clearly, because you're going to need to know this for the rest of the topic. So there are like two input wires going into a rectangular shaped main body, and from the main body we have one output emerging. Interestingly, one of the inputs is like negative and the other is positive. And you might get the wrong idea. The negative means this is getting say negative voltage, and the other one is getting positive voltage from the wiring to which it is attached. It's not like that, and what it's actually like, you're gonna learn in a bit. So the negative is inverting input, and this is something you can actually really get a bit confused about. You'll forget which one is inverting, which one is non-inverting. Right now, at this moment, you don't need to know what that means, but you do need to remember which is called the inverting and which is called the non-inverting. So let's say inverting a child, is that a good thing or a bad thing? A bad thing. So it's negative. That's the way I remembered it. So inverting signal is the one that is received by the input that is classed as negative. So it's the inverting signal or the inverting input. And then the other one is the non-inverting signal or the non-inverting input. Right, so then we have the output, and then there's these sort of like sticks that are projecting off from the triangle, and they're like written as being positive or negative. Are they like receiving positive voltage from one side and negative from the other? Nah, it's actually referring to the fact that the op-amp is actually connected to a power supply, and this part of it is connected to the positive part of the battery, and this one to the negative side or the negative component of it, or the like. So that's why it's called as being negative. It's not actually receiving negative or positive input. But again, it's not quite as simple as that either. And this is actually, this positive and this negative is actually what is running the op-amp, so that it is able to process the inputs that it is receiving, that is the inverting and the non-inverting, in order to give up a output, right? Right, so this can literally do a lot of stuff, so it's pretty handy, and it can be manipulated in different manners, so it can carry out different operations, so that it can do different stuff, so it's pretty versatile. So what can it do? So make a functions title on your notes and write act as a switch when voltage reaches a certain value. That's interesting, right? What voltage? Which voltage? For now, you don't really need to worry about it. A certain threshold. So it's basically really important, because that's like the basis of sensing and output, or the basis of homeostasis. It amplifies both DC and AC. So its amplification And remember, they're saying voltages and not current, so don't write current. Amplification of AC and DC voltages. And that's something it can do. It can compare to voltages. Like the voltages that it's going to be comparing are the inverting input and the non-inverting input, right? And the output is going to be a result of that comparison. So comparison of two voltages, right? Comparison of two voltages to give an output, right? That's important. And when an op amp is being used to do that, it's said to be a part of a comparative circuit, and we're gonna really study this one in detail, and this one is actually really important. And now you're gonna be like, I'm telling you so much weird stuff, so where are the properties? Don't worry, here they are. So now we've done a basic idea of what it does, what it looks like, what its components are, and the functions it can serve. And it can serve a lot of functions because it's a very versatile electronics device. So properties. And at the moment we're talking about the properties of an ideal op amp, and I really cannot emphasize that enough. So it has something that is called infinite input impedance, and impedance is like it's really just resistance. So what they're saying that at the input the resistance is an infinite, and when the resistance is infinite, no current will enter or leave the ideal op amp because the resistance is infinite. So on your diagram which I asked you to draw, take a pen of a different color and point towards the input terminals, either of them or like both of them, and write down infinite input impedance. And like be careful about the spellings of impedance, I get them wrong. And then in a bracket you can write no current enters or leaves the op amp. Right? So let's think about it. So if we were to connect an input to one of the resistors in a potential divider, what does that mean? You know what a potential divider circuit is, don't you? There are simple ones and there are more complicated ones that integrate a resistor whose resistance isn't constant. So if we were to connect the input to one of the resistors in a potential divider, the input would be in parallel with the resistor, and therefore the resistance in the potential divider circuit would be changed. Why? Because we'll have like two resistors that are in series to each other, right? And like one of them can have a constant resistance and the other can be a variable one, and they're connected to a power supply, a constant power supply, and because of them being in series, the potential difference is sort of like divided. But if we were to connect an input to one of the resistors, the input and that resistor would effectively be in parallel to each other, and so the overall resistance of that potential divider circuit would change, and so would the value of the potential difference that would drop across that resistor. Obviously the total PD would be the same, but the distribution of the voltages would be different because the input in parallel would be changing the resistance. So if you were to connect the op amp to the potential divider, then the potential difference across the components in the potential divider would change. However, if the op amp connection has infinite resistance, then connecting it to the potential divider will not affect the potential difference. Why? Because when we have two resistances in parallel and we want to get the effective resistance, it's 1 over R1 plus 1 over R2, and so initially we just had R1, but now we have R2 that is infinity. So 1 over infinity is 0, and 0 is literally gonna have no impact on the effective resistance. So it's not gonna impact the distribution of potential difference. So either right, this means a bit more detail so that you don't forget. You can write in brackets because 1 over infinity is just 0. So hopefully this makes sense, and this is the first property. So onwards to the next one. So while we had infinite input impedance, we have 0 output impedance. And you're like, what? Why? So where else do we hear about there being zero resistance? We talk about that in ideal conditions, the internal resistance of a circuit is 0. And what does that mean? It means that there aren't any energy losses across the wiring, across the inside the battery, and so all the voltage that is provided will be distributed across the actual components, and none of the voltage will drop about any unnecessary component that is wiring. And that's the same over here. All of the voltage will be transferred to whatever is on the other side of the op amp, and none of it will basically be across the output. So none of the voltage will fall across the output. All of it will be transmitted to whatever output device the op-amp is connected to. So let's write this down. Zero output impedance. Right. The whole of the output voltage is seen across the load connected to the output. All of the output voltage is seen across the load connected to the output. So it might be a resistor or something, and it often is. So if the output connection had some resistance, then the voltage produced in the op-amp would be divided between the output, that is where the output is coming, and the resistor that is connected to the output. So zero output resistance or zero output impedance means that all of the output voltage will be seen across the resistor connected to the output and none across the output itself. That's like important. It's the output itself. So that is like the second property. Moving onwards to the third one. This is about something called open loop gain. So what is that? That's basically the ratio of the output voltage and the input voltage. You might be wondering, don't we like have two input voltages? So how does that work? No problemo, and this is actually really related to why we call the inputs, one of them being positive and the other being negative, even though they're both receiving the same polarity of voltage. That's all going to make sense, right? So what does it mean? What does infinite open loop gain mean? We don't even know that. We just told you it's a ratio of something. What does that mean? That doesn't mean that if we have we have even a small input, the output will be really huge. That is what it appears to mean. Is that what it is? Is that what's going to happen? No worries, we're going to get on that soon enough. So this means that when there is only a very small input, the amplifier will saturate and the output will have the same value as the supply voltage. Hey, what does that mean? If the loop gain is infinite and we have a small input, doesn't it mean we should like have an infinite output? What's all this about it being the same as the supply voltage? What was the supply voltage? Yeah, we studied that, didn't we? Those positive and those negative. So what is this? What is this? Well, isn't this supposed to be ideal? What's logic doing over here? No worries. Let's first write the explanation down. Writing stuff down really helps me, maybe you too. When there is only a very small input voltage, the amplifier will saturate. And what does that mean? What is being saturated means? From chemistry, you know it's when you can't add any more salt to a solution, because any more just won't dissolve and would so precipitate out. And that's just it. The amplifier cannot amplify beyond a certain value. So even if the input is small, we're going to have the maximum amount of voltage that a particular op amp can possibly give. And the maximum voltage is limited by the supply voltage. If the supply voltage is 9 volt, then the maximum output that it can give is 9 volt. And the thing about infinite loop gain is that only even a small input can give us a huge output, but the output is still in fact limited by the value of the supply voltage. Cool, does it make sense? The amplifier will saturate, put this in commas, and the output will have the same value as supply voltage. So think about the maximum output being limited by the supply voltage is really important. So I'd suggest you write that down. And how do you write that down? You can write max output voltage is limited by the value of the supply voltage. So this is why you can really get, if you were to look at your notes, just why in spite of there being an infinite loop gain and loop gain being voltage output over voltage input, why we can't go beyond a certain output voltage. This is third. We still have I guess 2 more important properties to go over, so hold tight. And the voltage gain, or simply gain of an amplifier, is a measure of how many times the output voltage is greater than the input voltage. So it's V out over V in, that is by how many times V out is greater than V in. So when there are no components connected between the output and the input, meaning the whole op amp isn't connected to anything, it's just sitting over there, then the gain that is measured is said to be the open loop gain. So if they're going to ask you what's the difference between gain and open loop gain, you gotta know that. What is the difference? So voltage gain is a measure of what exactly? Is a measure of how many times the output voltage is greater than the input voltage. And open loop gain is the gain when no components are connected to the output or the input of an op amp. No components are connected to the output or the input of the op amp. So that's when the gain is in fact the open loop gain and supposedly infinite, but not actually, not realistically. Right? The output cannot be greater than the supply voltage because energy conservation. And so if a very small voltage is applied to the input and the gain is infinite, then the output will be at the supply voltage, and the output unfortunately cannot be any greater even for a larger input signal, because the amplifier is said to be saturated. And if they give a question as to why the output voltage is limited by the supply voltage, you can mention the concept of energy conservation, because that's why. Still two properties left. So here we go. So infinite bandwidth, and bandwidth is something you probably you learned about that in the communications topic, and you will probably be fuddled about it as much as you are going to be now. And what it means is that the bandwidth is the frequencies, and the bandwidth for a op amp are the frequencies that can be amplified properly, that can be amplified equally. And when the op amp is said to have an infinite bandwidth, it means that the op amp is really great at its job, and that any and all frequency can be amplified equally by it. So just as in the communications topic, bandwidth has to do with a range of frequencies. All frequencies are amplified equally. They're not, because when you're using a telephone, your voice is going to sound weird to the one who is on the other end, because your voice and the words that you're saying are going to have a lot of frequencies. Some of them will be amplified the way they should be, some won't be amplified the same, and so your voice is going to sound weird. This is important. Amplified equally. That is a technical word, and you should reproduce that. So if an AC is applied to the input, the output will have the same frequency at all points. Just the amplitude will be larger because you have amplified it. So for an AC input, or for an AC input's output, same frequency, but larger amplitude. But if it wasn't infinite, some of the frequencies would have been amplified a lot, and some wouldn't have been amplified. That is, the amplitude wouldn't have been increased by the same amount. That is why your voice would have sounded weird. So now infinite slew rate. So is that like the rate at which you're slaying monsters or something? It's not. It means the delay or lack thereof. So basically, if you have an infinite slew rate, there isn't any delay. But if you don't have an infinite, there's going to be a delay. And the smaller the value of the slew rate, the greater the delay. But what delay are we talking about? The delay for when we're getting onto a train, or when the train is going to come up. Now it's the delay at which there is a change at the input. That is, the input signal is changing, and the time it takes for the output signal to change to mirror the change at the inputs. So infinite slew rate. Measure the time delay between changes to the input and the output. So let's define it. Measure of the time delay between the changes to the input and the output. So that's cool. But what next? Is there anything else? So a high slew rate implies a short time delay. So you can write that slew rate is inversely proportional to the time delay in your notes. And with an infinite slew rate, there is no delay. And as I was saying, all of these are the properties for a ideal op-amp. So in reality, they are not ideal, and the input impedance, the one we talked about at the beginning, should have a value between 10 to the power 6 and 12 ohm, and the output should still have a value in the range of 10 to the power 2, even though it should have 0.